Okay, welcome group. This final lesson from chapter 3 looks at double displacement reactions. So it's similar to the single displacement, except the type of reactants are compound-compound instead of compound element. And there's a little bit more variety in the types of products which can form. And whereas single displacement reactions, we were mostly interested in solid phase, metal elements, either reactants or products. In the double displacement, we're interested in aqueous, and particularly the formation of a precipitate. So this is a reaction involving generally two aqueous ionic compounds in which the two positive and negative ions rearrange to form new compounds. That would be what we call double displacement. The tricky thing with this type of reaction is that the general form is pretty easy to understand. It's a double displacement, or a rearranging of both elements from both compounds. So we're just really recombining green with brown or blue with purple. We could think of it like that, or in the general form above. Element A now takes the place of C and vice versa. But the thing with the writing of the reaction equation is that the reaction doesn't always happen. In order for a new substance to form, we have to get substances with new chemical properties or new physical properties. And if that doesn't take place, then all we've done is we've just mixed two solutions together and we just have a mixture. So we have ways of predicting whether or not the products will form. This introduces one of the tables you'll see in your handout, which is found in the textbook on page 137, and it's shown on this sheet of your package, which is the solubility table. The solubility table can be used just simply to predict whether or not a given combination of a cation and an anion will in fact be soluble. That is, can they be dissolved easily in water, or will they have what's called low solubility, in which case we're quite likely to either dissolve very little, or on the other hand, we could be looking at what if these two ions combine in solution, will there be a reaction as products? Let's go back to our first slide here and just extend this idea of double displacement to the three possibilities, and these are outlined in your textbook. So the three possibilities that can exist are, as has been mentioned, a solid precipitate can form in solution. As an example there is given, calcium chloride combining with sodium carbonate to produce calcium carbonate, which is largely insoluble. Some will remain in solution, but most of it will precipitate out, and so we'll get definitely solid calcium carbonate crystal. Sodium chloride as a product will remain fully dissolved because it has high solubility, and as a product we won't really see evidence of it. Second possibility is that a gas is produced. So in this case, we still have two compounds involved, two aqueous ionic compounds, and this could possibly form a soluble ionic compound as well as a molecular gas. There's one possibility shown there with the production of dihydrogen sulfide. The third possibility is that we get a more traditional acid-base type reaction, which also fits that description fairly well. Two ionic compounds, although in this case hydrogen chloride, aqueous hydrogen chloride, is molecular, but in solution it would exist as ions once it's dissolved. Magnesium hydroxide, again, could start out with the solid form of the compound, but it's highly soluble, and so it will dissolve, and so we do have aqueous ionic compounds. And the results there could be a salt and water, one of which, in this case with magnesium chloride, is highly soluble, and the other could be a molecular liquid such as water. All right, so we have acid base, so we have the production of a gas, and we have the formation of a solid precipitate. Now, in order to predict whether or not the precipitate will form, we need to refer to a solubility table. So when a precipitate is expected to form, it's because the compound has low solubility. So the presence of those two ions together have low solubility, meaning very little of them will remain as aqueous ions freely moving in the solution. They will bond together ionically and form an ionic crystal. Those that have high solubility will likely not be observed. We would not call that that product a new substance because we still just really have free-floating ions in solution. For example, chloride in the presence of sodium. They won't bond to form sodium chloride with lots of water around. Sulfate in the presence of potassium. Again, they will not bond. They'll remain fully soluble. They're not chemically attached to one another. We don't associate them as a pair, so we don't call it a precipitate. We don't really even call it a product. Nitrate with any cation has very high solubility. There are really no positively charged ions that will actually precipitate in the presence of nitrate. So again those types of combinations, it's not just each ion on its own, but those types of combinations are not going to produce a precipitate because they have very high solubility in the presence of the other. So these types of ions which were bonded previously with a reactive ion, so why are they in solution? Well, they were in the solution. For example, in the case of sodium carbonate, well, sodium needed to be there to provide a source of carbonate. Calcium, or chloride rather, chloride needed to be there to provide a source of calcium. Now, calcium in the presence of carbonate has very low solubility and will precipitate. Sodium in the presence of chloride will have high solubility and will remain dissolved in aqueous form. So we would call those non-participating ions in these types of double displacement reactions spectator ions. They're just there sort of watching as spectators at a sports match do. They may have driven the athlete to the arena or out to the field, but they're just going to sit and watch. Okay, so you can think of that analogy. So spectator ions do not participate in the reaction, and they don't form insoluble products or precipitates. So referring back to the solubility chart here, again, the way it works is you're looking on the left side, the cations. Okay, there's two categories. There's high solubility and low solubility. High solubility remains as aqueous ion, or aqueous ionic compound, and a low solubility would refer to a precipitate that would form. Now there's sort of numerical cutoffs here, which later we'll understand a little bit more, but generally 0.1 as a unit of concentration. If the solubility is less than 0.1 in this unit, which is called a mole per liter, so that much solute in a liter of solution, that's described as having very low solubility, low or very low. Anything that can be dissolved in a greater concentration than 0.1 units of solute for every liter of solution is classified as having high solubility. So it's not to say that it either never dissolves or always dissolves, it's the relative amount. So we can use this chart here to predict the products for the following two reactions. So here's some example we can go through together. So let's suppose we were to combine aqueous ammonium phosphate with aqueous iron 3 nitrate. Okay, so we're naming those, and we want to predict whether or not a reaction will even occur. And if so, what would be the products? Well, we're looking at the ions present, and we can list them. We have ammonium ions, we have phosphate ions, we have iron 3 plus ions, and we have nitrate ions. Okay. Now, having poured those two solutions together, we now have the potential for new insoluble products to form. Okay. In the presence of each other, they seem to be highly soluble. We can use that chart to actually confirm that iron 3 nitrate is very easy to dissolve. All nitrates will have high solubility. Now what about phosphates? Well, phosphates are in the group of carbonate and sulfite, and we see there that anything that has a positive charge found in group 1 or ammonium will have high solubility. So again, ammonium phosphate would be easily dissolved in water. All right, so we have these two solutions which on their own are fully soluble. or very easily dissolved. And now we want to combine them together and predict a reaction. Okay, so iron in the presence of phosphate. Now, is there a possible reaction there? We see here that most phosphates have low solubility. That would obviously include iron 3 plus. So that means that iron 3 ions in the presence of phosphate will probably form an insoluble precipitate. Of course, nitrate has high solubility with any cation. So nitrate in the presence of ammonium, which is included in the all category, would obviously have high solubility. So our predicted products would be aqueous ammonium nitrate, so 1-to-1 ratio for ions. Even writing the chemical formula of that in aqueous form is not suggestive of the fact that a new compound is formed. Rather, we would understand that we still have free-floating ammonium and nitrate ions, which are really not associated with each other. We can write this theoretical product, but in fact, because it has high solubility, we won't form any new chemical properties with the combination of those two. However, iron 3 phosphate, we will. Because phosphate and iron both have balanced valences, the chemical formula of iron 3 phosphate would be FePO4, which, because it has low solubility, we would indicate as having a precipitate formed. This is iron 3 phosphate. Okay, and our spectator ions would be these two here. Okay, they were there because they were paired with the reactive ions phosphate and iron 3, but they themselves don't react together. Let's look at copper 2 chloride and sodium sulfate. Again, sodium sulfate is aqueous because sulfate over here has high solubility for most cations. Sodium is in that category because it's not listed below. So that's confirming the low solubility, aqueous form of sodium sulfate. Copper 2 chloride. Chlorides are over here. Okay, chloride again, high solubility for most cations. The ones that are not highly soluble are silver, lead 2, thallium, dimercury 2 plus, mercury 1, and copper 1. So copper 2 chloride again, high solubility. Now, pour those two solutions together, there's potential for reaction. As we saw before, chloride has high solubility with most cations, and in the presence of sodium, will form a soluble product. So one of the products will be sodium chloride, which, because it's aqueous, we can write theoretically, but in fact, those are spectator ions which won't associate to form a precipitate. And the other possibility for double displacement, which would be sodium kicks out copper, or we could say copper kicks out sodium, and in this case, both displaced to new compounds, we would have copper sulfate. And in this case, it would be copper 2 sulfate. So if you're wondering about valences for multivalent metals, the valence typically does not change in a double displacement reaction. So if it's copper 2 plus in the reactant, it will be copper 2 plus in the product. That's really important because when we're predicting the product copper 2 sulfate, we need to know that it's not copper 1 sulfate. It would have a different chemical formula. Sulfate has high solubility for most, but if we look below low solubility, we see that copper 2 plus is not included in that list. Therefore, in this case, copper 2 sulfate would also be aqueous, which means the net effect is nothing happens. Very likely, nothing occurs. There will be no reaction, no precipitate. All our products are highly soluble, and so that's our conclusion. No reaction, meaning no precipitate does not form. Okay, so we're starting to use this solubility table to both predict the solubility of a given compound as well as the potential for the formation of new compounds in a double displacement reaction. Here's a a little black line master showing some laboratory equipment, and because precipitates are often formed, usually they're formed because they're desirable and they can be separated from the solvent in the solution as well as the other ions through filtration. And so we see lots of equipment listed on here. And towards the bottom we see some of the equipment associated with filtration, possibly a funnel rack. We may be using an evaporating dish once the filtrate has been separated. Maybe we want to evaporate the water and capture the insoluble ion in that. Quite often we might be using clamps and different equipment. This second visual here also shows some equipment associated with filtration. We have a retort stand, we have our clamp, we have a funnel, we have some filter paper, and a collecting beaker with possibly a wash bottle to filter or to rinse our filter paper. We'll do some of this type of lab work in the class where we'll use filter paper, and some of you have maybe practiced folding filter paper and setting up a filtration apparatus and pouring the solution off to separate the insoluble product. And so those are some pieces of equipment which we'll have a chance to use in the classroom. Just a couple of video clips I want to show you here just to illustrate just how rapid precipitate formation is. You may not have observed or witnessed these types of reactions before, but generally if the reaction is going to occur, it happens immediately, and it happens very rapidly, and the amount of precipitate formed usually occurs within the first few seconds.
In the test tube, we have an aqueous solution containing iron 3 ions. To this, we will add a solution of sodium hydroxide. A precipitation reaction occurs that produces iron hydroxide, an insoluble metal compound. A solution of lead nitrate is added to a solution of potassium chromate. A yellow precipitate of lead chromate forms, leaving potassium nitrate in solution. The potassium and nitrate ions do not take an active part in the reaction.
Okay, so as you saw in that first clip, the two solutions were aqueous. So you take a little eyedropper and you take a certain amount of each. Sodium hydroxide has high solubility. Iron 3 nitrate has high solubility. We can verify that from our solubility chart. So the hydroxides are highly soluble for group 1, as well as ammonium, strontium, barium, and thallium. So sodium is group 1 cation. On the other hand, we have nitrates, which have high solubility for all cations. So getting those two compounds into solution is easy. The predicted products for double displacement would be sodium nitrate, which again will have high solubility because all nitrates are highly soluble, and iron 3 paired with hydroxide has low solubility. We find that again in our solubility table, where we see that most hydroxides have low solubility. Less than 0.1 units of solute for every liter of solution will dissolve, which means we will see precipitate. Some iron 3 plus and some hydroxide ions will remain in solution. So it's a little bit misleading to say that these are our products, aqueous ions. That's pretty much confirmed. No precipitate will form likely unless the concentration is really close to that sort of divider of 0.1 moles per liter. But for now we can predict aqueous and the product of iron 3 hydroxide as being solid. In reality, we would still have some aqueous iron 3 hydroxide. There would be some Fe plus 3 ions and some OH negative ions in solution, but most of it would precipitate out. So we usually do not include this information, but just keep that in the back of your mind as you're writing these reaction equations, that there will always be some amount of the compound that will dissolve, because low solubility does not mean no solubility. Again, we want to make sure this is balanced. So going through here, we have 3 nitrate groups on the left side, we should have 3 on the right. Let's rebalance our sodiums. And if you've written the chemical formulas correct for all compounds, you should be balanced at this point. hydroxide can be balanced as a group because it's found in both the reactant and the product side. There's some work we can do in class now that you've viewed this video with a partner, and then independently some questions that look at double replacement, as well as some that have you go back and review the sections on single and double replacement on page 143. See you in class tomorrow.